Hi, welcome to the Shiko Math Lab Mathematical Statistics Problem Solving session. And today we're going to take a look how about estimator is a biased estimator for the parameters. And how do we prove this biased estimator is a consistent estimator? Okay, so here is the problem we're going to deal with. So let's show that x+1 over n+2 is the biased estimator for the binomial parameters here. Is this estimator asymptotically unbiased? And then show this is a consistent estimator for the binomial parameters P here. All right, let's go ahead and start here. Okay, let's go to our whiteboard. Okay, so the first things here, because I know the x here is binomial NPs, right? Okay, so now we want to take a look at this estimator. So is x+1 to the n+2 here. Okay, so let's take a look at the expected value. So expected value, just take the n+2 out, and then this is expected x+1. Okay, so the expected x+1, so I know that this is n+2, then expected value of x is np, the expected value of the 1 just by itself, so it's np plus 1 over n+2, see here. So for this estimator, so let's take a look at what is the bias for this estimator. So the bias for this estimator will just be the np plus 1, the n+2 minus p, right? Okay, so here will just be the n+2, np plus 1 minus np minus 2p. So np cancel. So this one's here is limit. Oh, no, sorry, not a limit. So this one's here will be just the n+2 and the 1 minus 2p's here. So the second part is, okay, so this is the bias. Then they want to find is this estimator is asymptotically unbiased. That means, let's see here, if I let the n approach to infinity, what happened to this bias here? So if I let this bias n approach to infinity, so this is 1 minus 2p n plus 2. So what happened when n approach to infinity? The denominator approach to 0, right? So I know this approach to zeros here. So I know this estimator here, x+1 plus 2 is asymptotically unbiased because of the biased approach to 0. All right, so now the next question here, we want to see if this is a consistent estimators here. Okay, so how do we do consistent? We have the two conditions, right? So we said the limit n approach to infinity if the bias equal to 0 and limit an approach to infinity, the variance of whatever your estimator is approaching to 0 here. So we already show this part, right? So the bias of this estimator is approach to 0. So now let's take a look at the variance of this estimator. So this is the variance of n+1, the x+1, right? So this will be the n+1 to the square, the variance of x+1. And you add the constants, doesn't matter. So this is n+1 to the square. So this have a variance of x. So if x is a binomial, so what is the variance of x? Is we're going to be np 1 minus p. So this is n+1 to the square. All right, so now let's take a look at the limit n approach to infinity, variance of x+1, n+1, that will be equal to the limit n approach to infinity. This is n+1 to the square, NP1 minus P, see here. So take a look here. This is the square term for the n. So this is only n to the first power, right? So the denominator going to the infinity way faster than the numerator. So what is the whole thing approach to? The whole thing approach to zeros here. So now we prove the bias here equal to 0 from this equation. Now we also improve the variance approach to 0. So what is our conclusion? So I know this estimator 𝑋+1 over the 𝑛+2. This is what? This is a consistent estimator for what? For the binomial parameter P here. All right, that's it. So this is a pretty easy problems here, but the key things will show you, if you have a estimate is a bias, and if you can show the bias is, if you can show this estimator is asymptotically unbiased, and then you can apply the variance of the VT equal to 0, then that's, you'll be able to show this is a consistent estimator for P here. All right, that's it. And hope you this easy problem help you to understand consistent estimator and asymptotically unbiased mean. All right, so the nice talk to you and looking forward to work with you our next problems here. Okay, bye bye. Have a good day. Bye.